The structure and properties of solids. In this video, we are going to look at four types of crystalline solids: metallic solid, ionic solid, covalent solid, and molecular solid. In both elements and compounds, the structure and properties of the solid are related to the forces between the particles. Although all forces are electrostatic in nature, the forces can vary in strength. What we observe are the different properties of substances, and we classify them into different categories. To explain the properties of each category, we will use our knowledge of chemical bonding. Here is a table to outline the categories of substances. We can have ionic, which is between a metal and a nonmetal, and I've given you some examples. Metallic bonding, which is between metals. Molecular, which is between nonmetals. And covalent network, which is between metalloids and carbon. So let's start by looking at the ionic solids. Ionic bonding is defined theoretically as the simultaneous attraction of an ion by the surrounding ions of opposite charge. The full charge on the ions provides a greater force of attraction than do the partial charges on polar molecules. In general, then, ionic bonding is much stronger than all intermolecular forces. Ionic compounds in their pure solid form are described as a 3D arrangement of ions in a crystal structure. And I have given you an example here of a sodium atom and a chlorine atom. These properties are interpreted to mean that ionic bonds are strong, evidenced by hardness and melting points of the solid, and directional, evidenced by the brittleness of the solid, and that the lattice is composed of ions as evidenced by its electrical conductivity. Ionic compounds are relatively hard but brittle solids at SATP, conducting electricity in the liquid state but not in the solid state, forming conducting solutions in water, and having high melting points. Metallic crystals. Metals are shiny, silvery, flexible solids with good electrical and thermal conductivity. The hardness varies from soft to hard, for example, from lead to chromium, and the melting points from low to high, mercury to tungsten. Further evidence from the analysis of X-ray diffraction patterns shows that all metals have a continuous and very compact crystalline structure. With few exceptions, all metals have closely packed structures. Metallic crystals continued. The properties of metals are the result of the bonding between fixed positive nuclei and loosely held mobile valence electrons. This attraction is not localized or directed between specific atoms as occurs with ionic crystals. Instead, the electrons act like a negative glue surrounding the positive nuclei. Valence electrons are believed to occupy the spaces between the positive centers or nuclei. This simple model, known as the electric sea model, incorporates the ideas of low ionization energy of metal atoms to explain loosely held electrons, empty valence orbitals to explain electron mobility, electrostatic attractions of positive centers, and the negatively charged electron C to explain the strong non-directional bonding. Here we have some properties of metallic crystals, shiny and silver. Valence electrons absorb and re-emit the energy from all wavelengths of visible and near visible light. Flexible, non-directional bonds means that the planes of atoms can slide over each other while remaining bonded. Electrical conductivity. Valence electrons can freely move throughout the metal. A battery can force additional electrons onto one end of a metal sample and remove electrons from the other end. Hard solids. The electron C surrounding all positive centers produces strong bonding. Crystalline. Electrons provide the electrostatic glue holding the atomic centers together, producing structures that are continuous and closely packed. Molecular crystals. Molecular solids may be elements such as iodine and sulfur, or compounds such as ice or carbon dioxide. The molecular substances, other than the waxy solids of large hydrocarbons and giant polymers, such as plastics, are crystals that have relatively low melting points, are not very hard, and are non-conductors of electricity in their pure form as well as in solution. From X-ray analysis, molecular crystals have a crystal lattice like ionic compounds, but the arrangement may be more complicated. In general, the molecules are packed as close together as their size and shape allows. The properties of molecular crystals can be explained by their structure and the intermolecular forces that hold them together. London dipole-dipole and hydrogen bonding forces are not very strong compared with ionic or covalent bonds. This would explain why molecular crystals have relatively low melting points and a general lack of hardness. Because individual particles are neutral molecules, they cannot conduct an electric current even when the molecules are free to move in the molten state. Covalent network crystals. Most people recognize diamonds in either jewelry or cutting tools, and quartz as gemstones and in various grinding materials, including emery sandpapers. These substances are among the hardest materials on Earth and belong to a group known as covalent network crystals. These substances are very hard, brittle, have very high melting points, are insoluble and are non-conductors of electricity. Covalent network crystals are usually much harder and have a much higher melting point than ionic and molecular crystals. They are described as brittle because they don't bend under pressure, but they are so hard that they sometimes break. Diamond, CS, is the classic example of a covalent crystal. It is so hard that it can be used to make drill bits for drilling through the hardest rock on Earth. Another example is silicon carbide, used for grinding stones to sharpen axes and other metal tools. Carbide-tipped saw blades are steel blades coated with silicon carbide. The shape and X-ray diffraction analysis of diamond shows that the carbon atoms are in a large tetrahedral network, with each carbon covalently bonded to 4 other carbon atoms. Each diamond is a crystal and can be described as a single macromolecule with a chemical formula of CS. The network of covalent bonds leads to a common name for these covalent crystals as covalent network. This name helps to differentiate between covalent bonds within molecules and polyatomic ions and the covalent bonds within covalent network crystals. Most covalent networks involve the elements and compounds of carbon and silicon. Crystalline quartz is a covalent network of SiO2. Glass shares the same chemical formula as quartz but lacks the long-range, regular crystalline structure of quartz. Purposely, gas is cooled to a rigid state in such a way that it will not crystallize. The properties of hardness and high melting point provide the evidence that the overall bonding in the large macromolecule of a covalent network is very strong, stronger than most ionic bonding and intermolecular bonding. Although an individual carbon-carbon bond in diamond is not much different in strength from any other single carbon-carbon covalent bond, it is the interlocking structure that is thought to be responsible for the strength of the material. This is similar to the strength of a steel girder and the greater strength of a bridge built from a three-dimensional arrangement of many steel girders. The final structure is stronger than any individual component. This means that individual atoms are not easily displaced, and that is why the sample is very hard. In order to melt a covalent network crystal, many covalent bonds need to be broken, which requires considerable energy, so the melting points are very high. Electrons in covalent network crystals are held together with either the atoms or in covalent bonds. In either case, they are not free to move through the network. This explains why these substances are non-conductors of electricity. Other covalent networks of carbon. Carbon is an extremely versatile atom in terms of its bonding and structures. More than any other atom, carbon can bond to itself to form a variety of pure carbon substances. It can form 3D tetrahedral arrangements, as in diamond, layers of sheet graphite, large spherical molecules, buckyballs, and long, thin tubes, carbon nanotubes. Graphite is unlike covalent crystals in that it conducts electricity, but it is still hard and has a very high melting point. Graphite also acts as a lubricant. All of these properties, plus the X-ray diffraction of the crystals, indicate that the structure for graphite is hexagonal sheets of sp2 hybridized carbon atoms. Within these planar sheets, the bonding is a covalent network and is therefore strong. But between the sheets, the bond is relatively weak due to London forces. The lubricating property of graphite arises as the covalent network planes slide over one another while maintaining the weak intermolecular attraction. The electrical conductivity arises through the formation of pi bonds by the unhybridized p orbitals. These pi bonds extend over the entire sheet, and electrons within them are free to move from one end of the sheet to another. Properties of ionic, metallic, molecular, and covalent network crystals. So this is a summary chart that will provide you with some information as you complete your lesson. So the crystal is ionic, particles are ions, force bond ionic, properties hard, brittle, high melting point, liquid, and solution conducts. And I've given you some examples. Metallic, cations, metallic, soft to very hard, solid and liquid conducts, ductile, malleable, lustrous. Molecular, molecules, London dipole-dipole hydrogen, soft, low melting point, non-conducting solid, liquid, and solution.